Hello, everyone. Can you hear me?
Good morning, Professor Tan.
I cannot hear you. What's wrong
Oh,
with this PC?
um, can you hear me now?
Hello, hello. Can you hear me?
Hello. I can hear you.
Uh, I'm not sure it's your problem or my problem. Let me check. 1 second. Okay, it looks like my problem. Okay, there's some problem with my speak. Let
Can you hear me right now?
me. Oh, I can hear you now. Yeah.
Oh, can you hear me?
I can hear you. Yeah, something wrong with my computer, so that's why.
Okay. I can
Uh,
hear you clear. So
sure.
yeah, thank you. Thank you for your contribution. So can you see this ESWIC logo from the participant?
Yeah,
Yeah.
I
So,
actually see you, but yeah.
mhm. If you look at the participant list, there is a one person who is named ESWIC underscore codes plus ISSS. And
Yeah,
she's
I
a
saw it.
college student. Her name is Barsika. She will be here to offer some help if you whenever you have some technical difficulty or something. So feel free to
Sure.
ask for help. And I will try to be here, but I will be moving around different Zoom sessions. So if anything
Okay.
comes up, please
Sure.
let her know, and we will do our best to help you. So Um, you may start, and as I wrote in your email, in the email, you may introduce yourself. Sorry for that, we don't have a session share for this education classes, and you may share your screen directly from your computer.
Okay, let me share my screen. Can you see my screen?
Yes, something is coming up. Yes, I can see your screen very clear.
Good.
Thank you.
Okay. Um, okay. Um, sure. I can start, right? Okay, looks like they don't have a moderator, so I will be the one who going to moderate myself. Hello everyone, my name is Yan Chen. So this is new to me and also I believe also to Yes Week to give this education courses. So the topic, for this particular lecture will be efficient and robust edge AI software, hardware, and the code design. So we have about 10 people here, I believe. So we have relatively small group. So feel free to interrupt me if you have any questions. So we're supposed to have a 2-hour lecture. So I believe nobody can to stand for 2 hours. We're probably gonna have a short break in the middle. Let's say somewhere about 15 minutes, we can have a short break and then we can to continue. Okay, let me see. Okay, so I love this picture because this picture originally came from a book, published more than 30 years ago. So the title of the book is The Age of Intelligent Machines, which was written by the Dr. Raymond Kurzweil. He actually calls himself as a futurist, which means the researcher who is doing research about future. Okay, it's not really technical. So he plotted, um, the available computing power on single electronic device over the years. As you can find out, if we compare about how many neurons we can have on one creature, and also the and also the device, we pretty much can offer very similar power, computing power equivalent to the human brain now. So this is actually a very powerful tool, allow us to do many things we could not do in the past. So this also directly draw the hype of the AI in the past couple of years. So if you look at the full stack AI design on the edge, or in general on all this AI system, so innovations happening everywhere. Started from the new material and device, people are able to build up the more efficient representation of these neurons, synapse or something first. And people can build out the circuit to compute the basic operation of the neural networks. And people also come up with architecture which is able to run those things on the software foundation. And there are some code design methodology need to be deployed, so people can optimize the computation more efficiently. And I believe you're familiar with this this research, because this has been very hot topic in the last a couple of years. And if you look at the partitioning of the AI hardware or the edge devices, people may not be able to use a GPU, because GPU can be very powerful, but can be also power hungry. So but it can be used to train the model, and people usually going to deploy the model on the edge device and train the models more efficiently, or maybe fine-tune the model on the edge. IPGA is a widely used hardware on the edge, and particularly for the reconfigurable applications. It can provide a very quick, the development cycle, but it generally have, the relatively less computing capacity than the GPU. And if you really have the large volumes of the application and also requiring the very high power efficiency, people are going to develop their own chip, which is highly optimized for some applications. And of course, there are many other novel architecture like a spectrum neural network or residual computing, and also the emerging devices like a spintronic, residual memory, or that kind of stuff, have been developed to push the boundaries of the compute. So you may be also familiar with the von Neumann bottleneck, right? So traditionally we decouple the computing and the storage. And each time we have to load the memory from the memory or for the cache to the computing unit, and it can compute. And the gap between this computing power and also the memory bandwidth is significant. So that people now trying to use this for non-von Neumann architecture, so which means people trying to have a very local data storage for the computing unit. They don't have to load the data from very, very far, or people can directly just compute in the memory. We'll show you later on. And also another one is we call the power wall, which means we're not be able to further scale up the clock of frequency, because we are not able to bring the hit out of the chip. So rather than we keep increasing the clock frequencies, people start to look at the solution to increase the threads, or even the cores on the chip, to increase the part of them. Okay, so we talk about the memory wall, or the von Neumann bottleneck, which means we don't want to load the data from the memory to the computing unit. So what we can do is we actually come up with the near memory computing paradigm or the in-memory computing paradigm, as we show here. Many people are actually doing this. So the basic idea is we're actually going to move the computing unit close to the memory, or we just directly compute, the computation. Most likely will be the multiplication in the memory file, so that we don't have to move data around. So this actually will contribute to one major component into this talk. Okay, so what I can do? We'll basically talk about the three things today. The first one, the code design for the efficiency. The second one, the code design for the robustness. Both are the hardware. And then we'll talk about how we put everything together, especially on the system level, how we're going to be able to build up, the secure and efficient Azure AI system. And we'll conclude the talk. Let's talk about the circuit design for the processing in memory or computing in memory, and as we just mentioned it. In the neural network, the basic operation is actually nothing else but the multiplication between the vector or the vector and the matrix. All this operation like convolution, attention model, so on and forth can be eventually represented as such multiplications. But traditionally, we have to build out the multiplier array, and we're going to send the data in and we compute them. Or we can come up with some very complex, the timing flow to guide the data flowing in this array, like we show in the cyclic array. But can we do something more efficient? For example, can we really compute everything, where we going to store the parameters of the neural network? And that was the idea. So in this particular design, for example, if we are able to build up an array of some device whose resistance can be used to represent the weight or the parameters of the neural network, we may be able to inject the voltage into this array, and then we drain the current along each column. If we carefully, formulate the computation, the input will be the voltage, and the conductance of this device will represent the weight, and the collected current along each column will naturally be the sum of the dot product between the input and also the resist or the conductance of the device. In other words, we actually can compute this n by n computation and the dimension of the input in one shot. We basically reduce the computational cost or virtually from n squared to 1. So that's the basic idea called the crossbar-based computation. We actually did this many years ago to talk about this. And in 2008, people actually came up with what we call the memristor crossbar, which was originally used for the storage. People can have, access the individual device in this crossbar. And we realized we actually can use this crossbar for the computation. That was the paper we published in about 2021 or 2020, 2012 or 2011 to come up with. Of course, you can program the device by doing this. So this was one of the earliest paper published in the world, talk about this. Okay, so after that, we continue developing our design by using the different devices, including the spiking neural network or the level-based computation. Yeah, so there's a multiple big way to I think someone and source grain array and so on. But okay, sorry, I just mute him. So yeah, those are some chip we designed. We continue to taking out the chip, in the last couple of years. And this is the one chip we published in 2019 by collaborating with the National Tsinghua University in Taiwan. The basic idea is we actually have the RN device integrated on top of the CMOS, and we actually can basic compute this matrix vector multiplication, and we use that one to perform the convolutional neural network or fully connected neural networks on the first, by achieving relatively high power efficiency. And you actually can make a trade-off between the resolution of the computation. For example, you can have a 1-bit, a 2-bit, or 4-bit. And the higher resolution give you the higher accuracy by paying for the higher power consumption. So I don't want to go through the details, but many tricks and how you can balance the voltage, make sure you can eliminate the nonlinearity in the circuit design, minimize the variation or so on and so forth. But that was the one of the worst. Okay, so but you don't have to develop these things in the RN device. You can implement things in the ISRAN device as long as you are able to represent the weight by using the ISRAN cell. You can do actually in a different way. You can store the information in the digital form or in the analog form, which we call the analog, computing in memory scene, or the digital computing in memory, or the pin processing in memory. But traditionally, you have to use the ADDA conversion, which means if the output will be likely analog signal. So you have to convert this analog signal to digital, which can consume a lot of power, and we don't want this. So in 2022, in ISCC, we published another paper by collaborating with my former student, Bonan Yan from Peking University. So we came up with ADC list, the idea is we actually have a dynamic logic, to replace the ADC in the computation. Of course, there are some constraints. For example, we are not able to really handle very large the resolution, because the dynamic logic has their own drawback here. But we can dramatically reduce the power consumption and improve the scalability of such design, because the ADC is not just the power consuming, but also we're going to occupy very large area. So this is the table we show in our paper. The basically will achieve the highest energy efficiency at that time, 27 TOPS per watt, and with with some tuning function to achieve different performance with a different power consumption, or so on the first side we show here. Okay, so that was one the work. But you can actually represent the input, using the spiking neural network, a spiking signal, but not the voltage. So representing the input as a voltage is kind of vulnerable to the power supply noise, because whenever you have any noise, you start to see the input noise, and the input actually will represent the data. So there's some advantage of representing the data using a spike. For example, spike is pretty robust, and we actually can generate the different frequency of the spike, and also different amplitude, and even at a different time. So all this information can be used to encode the information which can participate in the computation, as long as the signal is able to capture such differences. In this design, we published last year in DAG, we actually design this called spiking timing neuromorphic computing design using the conventional CMOS. The basic idea is we generate this spiking spiking signal, as we show here, and we actually generating the different time and the different temporal relationship between the different spikes, make a lot of sense for us, to incorporate the information into it. We call this a timing threshold, adjustment, which will give us this encoding scheme. We actually can also have the multi-level firing threshold adjustment, to really adjust this firing time of the activation logic, to adapt to the different, device variations, because we need to overcome this device variation. We could generate the variability in our output circuit. We can actually fine tune this the fairing threshold, which can store on the chip, so that we can have a better efficiency and also the better accuracy, but lower energy consumption. So those are the work which we have done in this particular circuit design domain. But there are many others. I just want to give you some examples here. Okay, so but if we have those circuit design, no matter going to be the voltage, going to be the spiking, going to be the CMOS, going to be the emerging devices, or so on first, we have to somehow incorporate this design into the pipeline design, which is the architecture can accelerate, the neural network or some other AI models. And you can also imagine that we have to have the compiler, support, to identify the portion which we can accelerate, and also, to dispatch those workload into the different component. So this is one example we published, 8 years ago in DAC. We call the Reno. So the basic idea is we have an in-house compiler, which actually identify the portion we can accelerate. So that you can imagine that will be primarily the vector matrix operations. And then we're going to map those things down to an array of this crossbar, and we'll show here. And there are actually multiple crossbars, form the one computing unit, so that we can freely represent the positive and negative input, and also positive and negative weight. Because it's so hard, to generate negative voltage, and there's no negative resistance of the device. So we have to do this trade-off. And we also have, the network on chip, which can guide the input and guide the output of the array, to the different, component, so that we can either map, the larger neural network layers into this hardware, or we can really implement the multiple layers, so that we're able to, to guide the data flow between the different layers, and then we can actually achieve very high energy efficiency compared with the traditional CPU or so on and so forth. So that was 8 years work, but still make a lot of sense currently, to show the prototype of such an AI accelerator array. But you can design actually very complex, the circuit or the pipeline. In another paper published, in the ASP 2018, that was best paper nomination, I believe. So you can actually find out a lot of data, a lot of redundancy in the current design of the GAN, or the generative adversarial network, which require two engines to coordinate. One will represent the generator, and the one will represent the discriminator. So you have to generate some, the samples and send to the discriminator, to detect if that can be the fake one, the real one, or synthesized one, and then you get the feedback, so that you can guide the generation of the samples in the generators. And we find out in this pipeline there are many stages are overlapping each other. They actually use the same pipeline stage and even the same input, the same output. They just give the different feedback with the training, by reading up different flag or the different labels at the output. So we eliminate this redundancy and achieve 30 times performance improvement. And in this another paper in 2019, the DAC, we find out there are another operation called a transport convolution is widely used in the generative network. Now it's a generative AI. So that we have to start with some seed, and we insert the zeros into this feature map, and then can create the larger and larger output. So eventually we generate something we want. And we can do two options. One is we just follow the algorithm. We insert the zeros, we do the convolution, or we do the convolution first, and then we insert zeros, because 0 times anything will be zero. This will be very important principle in the neural network and optimization, because even you will find out that there are many redundant zeros in this feature map, or the close to zero values, which we don't really need to compute them. So we actually swap the operation sequence of this in this transport convolution, so that we can dramatically improve the computational efficiency. Also in 2020, we start to look at acceleration for the transformer. You can see easily map the transformer on the CMOS design, but it's relatively hard to map the transformer into this emerging device-based design. So one reason is, transformer will generate a lot of intermediate result. And this immediate result need to store somewhere. And the writing operation in this emerging device, design is very costly. So in this design, we actually rewrite the operation so that we keep some intermediate outcomes until the end. So we don't need to store them somewhere until we really have to. And by doing so, we actually eliminate, one write operation out of the two operations we need in the conventional algorithm, and we actually improve the performance. And also we have the RM-based softmax in the design, which actually is also the very popular operation in this transformer design. So we can do more than that, in the in-memory design. Another example, we actually can have this recommendation system, so that we actually can chop the design to a much smaller array, which usually we don't want, because the fine grained inner product actually, if we map to the hardware, we have a lot of a small array, which have a very low energy efficiency when we're implementing this in the memory. But we can. That's why we need to somehow carefully manage, how many such a small array we need to map the copies, of the same. No, we're actually going to higher priority to the item with a higher access frequency, so that we don't have to have the, implement many such the basically high cost, the small array. And we also want to implement many copies, so to improve the paradigms of the computation. So there are many optimization we have done, and we actually came up with the 30 times speed up with the 60 times energy saving. That's a one paper we published in EC5 2021. But if you look at the AI accelerator array, usually in one AI chip, there can be the larger number of such AI cores, and we have to somehow optimize them. So, and we actually can use this array for not only the neural network, but also for the graph computing, because they pretty much share the similar architecture. In this design, for example, if no matter we're gonna do this the depth first search, or the width for the search, we can simply map those things down to this array, and the array just carefully control the computation sequence. Either we actually compute all the column, all the rows simultaneously, or just a column by column to mimic, the depth first computation. So by doing so, we can achieve a very high, energy efficiency, which which conventionally the graph computing is hard to accelerate, and still many graph computing computation are still used, the CPU, and we actually can map this down to the in-memory compute. But later on, Vijay Narayana from Penn State, his group contact us saying, actually, we omitted, one scenario, which we're actually quite familiar with. That is, there were a lot of zeros in the graph computing too. So they actually came up with another solution, which used a linked list to represent the computation and map them down to the CAN structure, the content addressable memory, rather than the conventional, in-memory computing matrix. And by doing so, they actually dramatically squeeze, the required computational cost from, let's say, 30 times or 50 times to 800 times. So this is actually very dramatic, improvement. And that was paper they published in the EC5. So they include us in the co-authors, but I should admit, it's actually I will give it 90% credits, to his groups on this. But I think that's worth to mention because it's a very excellent work. So, but if we have an array, we need to map the layers, to the different component. We call it P processing element. Traditionally, we have a two-way to partition the neural network. One is the data part of them, and one is the model part of them. For the data part of them, we're actually going to copy every, neural network. And we just, for different copies, we injected the part of the data or the input into it. For the model part of them, we actually partition the model into a different component. We send the data into it. So in 2019, HBCA, my student Linhao Song, he actually published one paper called the HYPER, which stands for the hybrid part of them, because he found out, it's not going to be optimal if we assign only one part of them into one layer. Actually, there are some layers that may deserve two part of them, because there are some throughput matching need to be done to maximize the computation of the P arrays. For example, in this particular figure, you'll see the black dot and the white dot. So a black dot means the model part of them, and a white dot means the data part of them. In the fully connected layers, we want to map, both part of the into it, to maximize, the throughput of this P array. So which makes sense. But in this the design, he actually exhaustively searched the optimal solution on this. But next year, he found out, there is another actually part of them which people are omitted for a long time, which is tensor part of them. Because when we actually calculate the feature map and the kernels, we're going to partition them to the different components. And in many cases, we just compute the feature map partially, and then we actually cluster. We're actually going to collapse them together. So which means now we have the three part of them: so data, model, and the tensor, which is going to generate 9 different combinations if we consider the input and output of the computation. So, okay, so that's hard to be handled by basically manually. That's why we're going to have a layer-wise partition. We'll have 3 different colors now. So data, model, and the tensor. We will decide how the layer will, be configured with the different layers of assigning to the different P's. And we could do the dynamic programming to do this. And also we have come up with a hierarchical solution, which will do the different partitioning until we can individually control the assignment of the different part of them, so of the different P's. And we show in the figure, we can have 3 different types of partitioning on the different P's belonging to the same layers. And we can achieve even higher, basically double the performance of the this P already compared with the high hyper we published a year ago. Yeah, that is the design. There's some. Okay. So any questions so far? Okay.
Thanks for your live talk. I have a small questions.
Sure.
You mentioned the design for the pin architecture for different neural network. This is for the ASCII architecture, but it's not generalized for the lot of models, isn't it?
For not general,
Yeah,
for what?
For GAN, there is one pin architecture. For transformer, they have another pin architecture. So this is not a generalized architecture. Is for a specific purpose. For example, if one machine it has one accelerator, it should embed a lot of accelerate into the machine, isn't it?
Yeah, it's a very good question. So how we can balance the generality of the pin design, because we have such a complex control logic, and also the specific, although maybe the efficiency. So answer is, we can actually design the very general design, which we need to lose some efficiency, or we can customize the design to improve the efficiency by losing the generality. So there are not one way or the other. So that's more engineering problem. And in reality, for each product, they only support some neural network, but not all of them. And they will have a CPU aside. So if there is a neural network that they cannot handle, or at least directly handle by the accelerator, they will somehow use the CPU to pre-process or just directly computing them. Yeah, so that's usually what you're going to do. Yeah.
Okay, thank you.
Yeah. Sure. Okay, so but there are many other ways, which we could do on this. For example, we can actually optimize the models. There is remember we talk about sparsity of the neural network, which means we have a lot of zeros in the neural network. So what are we going to do, right? In 2016, people actually saying, and from multiple groups, but the most famous one is Song Han or Bill Daly's group, saying they can they ignore the computation between 0 and any others, and if they do so, they can dramatically improve the performance and efficiency. By the way, it's actually not new in the neural network design, because of the sparsity of the neural network and reduce the computational cost that has been there for many years. But what their contribution is actually re-identify the problem and present it, from the hardware perspective. But at that time, if you carefully read the papers, and the paper basically showing about the theoretical or algorithmic speed up, which calculates the flops, but they never show you the real performance improvement. The issue is very simple, because if they just follow the sparsity of the neural network and they skip those computation, this zero width distributes randomly on the neural network and store in the memory randomly. So if we skip those computation, it's basically harm the data locality in the computation, generate a lot of cache misses. And remember, the CPU and GPU, they heavily rely on the prefetch. They're actually going to predict, the data based on the current data being processed, so that they can preload the data. But if you destroy this data locality, it's basically generate a lot of cache misses. You have to really find out the nice available data from the lower memory hierarchy, which can slowing down the computation, as we show in the figure 1. So here the speed up, so speed up is below 1, which means it's actually slowing down the computation. And the first several layers, can be very large. So that basically generates a negative speed up. So when we look at this problem, because we are the computer architect, we immediately realize, one simple solution is to perform the pruning of the neural network in the structural way, so that we can preserve the cache locality. It's a very simple solution. And we can still store those data structurally in the memory or in the cache. Now the problem becomes how we can do it. So structural pruning is not new again. So in the past many years, the neural network, research community has done a lot of works, theoretical works. So we can apply the group lasso, which means we can group, all this component with belonging to the same structure, so that we can prune them simultaneously. We can remove the filter and then the channels as a structure, or we can even remove the width belonging to the same location at a different kernel, because we know they store at the same columns in the memory. And by doing so, we can preserve, the cache locality, and we can improve the performance, as we show here. You can apply this one to not only convolution layers, but also to the LSTM or many other neural networks. So now the structural pruning has been the standard technique in almost all the neural network processing. So, and supported by almost all the hardwares. This paper has been studied for more than 2,500 times, I think, or around it. Just a little bit more than that. So you can actually carefully guide the pruning process by applying different regularizers in this group lasso. For example, you can preserve the large weights, because the larger weight usually means more sensitive, and then prune the smaller weights. And by doing so, you are able to improve the performance, which means the accuracy, and achieve the higher compression rate. But there are many other technologies. This is one example, proposed by our student Huan Rui Yang in iClear 2020. But there's certainly many other techniques can do this. You actually can also optimize the memory footprint, because you don't have to store, the kernel values in the floating point 1. You actually can decouple the weight parameters into a polynomial of basically the combination of the coefficient times by some the basis. If you have this kernels, let's say you have a 3x3 or 5x5, you basically can map all this kernel width into this 9-dimensional space or the 25-dimensional space. And you actually can decouple each vector into the combinations of the basis times by the coefficient. And by doing so, you actually can further improve the storage efficiency by storing only the coefficient and also the basis of vectors. So each time you can restore, the kernel value back to the original data. And you can do the model reduction, because you don't really need to store, such accurate, the weights. You probably can approximate this with a smaller dimensional vectors, like we show here, to improve the computational efficiency and reduce the memory footprint. It's actually a very common trick, in the many other applications. You can do the quantization. We actually came up with the quantization method back to 2016 using on the IBM True North chip. but different from the traditional quantization, you can just directly quantize based on the training of value. We find out that you do not need to, or you should not actually, to train the neural network, for the targeted efficiency, target accuracy, and then quantize. You have to consider, the quantized neural network and the accuracy. So what you really need to target is the quantized neural network as the accuracy rather than the full precision neural networks, accuracy. So one simple example is what if you can only represent the data with 0 and 1? Are you going to train the neural network and then you quantize them? No, because what you need to do is you are trying to minimize the number of the weights, around the 0.5, because 0.5 is the value you don't know how to quantize them. So you're actually going to quantize most of the weight close to 0 and 1, so that you can have the higher accuracy in the quantized value. So that's one example. You can apply the technique to many other scenarios as long as you have to have concern the quantized value. It's actually been widely used in the later applications. And this was the two Best Paper nomination award from the ASDAC 2017 and also DAC 2016. You of course can do the mixed precision because the different layers may have a different requirement of the quantization. So what you can do is you actually can quantize them with the different quantized values with the different layers, and you can achieve overall high compression rate with a different precision on the different layers. You can do even more aggressively. So there's another paper I like to share, which is the mixed precision with a bit level sparsity. So rather than we just do the pruning on the weight, we can actually do the pruning on the bit of the weight. Because when we store the values in the memory, we actually store every single bit. And for example, traditionally, you can completely remove this weight or not. But let's say you have a 6 and 3 stored in one memory. Each of them need to be represented as 4 bits in this particular design. So then you will find out you don't really need to have the 0 as MSB, because all the bit will show up on the last 3 bit, right? And also for the 10 and the 4, you don't need the last bit. But you actually can do even more aggressively. You can say, what if we can to represent the 8 and the 10, and 8 and 11? No, we don't need the third column of the bit. So we actually can remove the whole column at any position to further reduce the footprint of the quantized neural network. So which we apply the group lasso in this particular case, so that we can remove the whole columns of the of the data if we find out we don't need to have this if we don't need to have this the whole column to represent the data show up in this block. This be very aggressive, the pruning. Rather than we just prune the weight directly, we prune the bit in the weight. Okay, and at any locations, not just a prune maybe the first several bit or the last several bit. Okay, so neural architecture search. There is another way, to optimize the neural network, which close to the pruning but not exact, which means we can automatically find out, the optimal structure of the neural network, which can give it the highest accuracy with lowest, connectivity or so on first. So it's actually not hard to understand, right? Because if we give a lot of options, like the library of all the components, we actually can automatically search, the optimal combinations of all this, all options that generate the neural network, which give us the best solution. By doing so, we don't need the people who are the experts, to understand the performance of the neural network, or to really design this neural network manually. But traditionally, the only issue is a high search cost, because the first paper, the DARTs, when they propose, they actually have it running for 2,000 GPU hours to find out the optimal solution for the neural network design, which is certainly unaffordable. So what are we going to do, right? So one way to configure the NAS design is we can construct the graph, which we call the directed isolated graph, to represent the neural network, as I will show here. And you can actually have the dot as our operation, and you have the line to represent the data flow between different operations. Or you can do the opposite way. That's fine. So you can have the search space, where you consider the different number of the nodes as a topological search space. If you have a possible operations as the candidates, you can add up on this, the architecture, and you can, concat the operation, combine the result from different layers, or you can just route the data to the different operations. And you can even select different operations options. For example, you can say, we have a ReLU, tangent, or something first. So which one will give us the best solution? You can try out and find out the best solution if you have enough time to try out. This is one example to show how you can optimize. Let's say we have one cell. Okay, the one cell will represent the one block you want to optimize. And there, what you can optimize will be the connectivity within the cell. So what you can actually randomly remove some connections within the cell to see if any of this candidate will give you the high performance. Of course, in many cases, you don't really train from scratch, get to make sure they can converge. You just have the proxy data side with proxy training, so they can really rank the candidates. In many cases, it will give you a good approximation about which one will give you the best solution. You will find out the best candidate cell topology and add them together. So that's we call it iterative shrinking to find out if you have this complete neural network, how you are able to shrink them down to the optimal solutions. But you have many ways to do it. You can actually exhaustively search for that one, which may not be the good choice. Or you can actually leverage what we're quite familiar with, which is the optimization of the neural network training. So, which we call the differential approach. So in the differential approach, you actually can represent, all these candidates with one vectors in this optimization space. And you can have these angles between the different vectors to represent their similarities, topologically similarities. So what you can do is you can search different candidates to find out, the best solution by using the guidance generated by the proxy evaluation. The difficulty here is the topological space is a descript, which means the vectors are not continuous, right? So it's not going to directly use the optimization process we have in the training of the neural network. So what I can do? We actually create the encoding scheme. We can encode this neural network structure to the topological vectors, and we will compute the MSE loss. We're going to compute the similarity by using the discrepancy between these vectors, which can show us how large the difference is, and which can also be represented as the angles. And we will calculate the accuracy of the different blocks and use that one to as our target, at our output, to compare with the target and to optimize it. So we have some score predictor. It basically means if you give us one block topology, we can predict the performance and give the feedback saying this can be the good or bad. so that you can actually convert the whole design from the discrete optimization to the continuous optimization, which can use this differential approach. Our results show that we only need a couple hours to finish the optimization, and we can receive very good result, which is very similar to the one received by paying a couple thousand GPU hours, but with much less, optimization costs. It's particularly suitable for the fast deployment or some small company that don't have the larger computational resources to save the power, save the cost. But this may not be the ideal case. The reason is if we were designing the neural network, we usually do not really design like this. What we can design is actually we scan the small neural network to see if this small neural network is going to meet our requirement. If not, we will actually increase the size of the neural network to see if that's going to meet our requirement. If not, we'll continue to increase. So we came up with another solution called auto grow. So basic idea is we actually came up with some growth policy of the neural network, which is manually define it. And we start with a very small neural network with a very small number of the blocks to see if that's going to work. So if not going to work, we actually keep increasing the size of each block, and also number of the blocks to improve it to see how that will work until we reach up, the performance we want. So the result is like this: we can pretty much, achieve the operator frontier of the trade-off between the computational cost and also the accuracy. But it's so hard for us to control where we're going to stop. So it's a good try, but there's still a lot of unclear questions we need to answer regarding what are the good policy and what could be the guidable policy which we can achieve, some target trade-off we want. Okay, so that's auto grow. The NAS can really generate something very powerful. This is one design we use for this visual recognition search. That was used for the computation, and we actually search for the best visual recognition search, visual recognition architecture by using the NAS, which can generate a lot of connectivities between different layers, which usually people are hard to develop because they're irregular. It's not like a very regular, connectivity which can copy paste or replicate. It's a very irregular search. It has to give us the best performance in that computation with number one in one category, but with the much less the computational cost, as we show in the semantic segmentation and the human cost estimation I will show here. Then this year in the 3W, we published another paper in the talk about the NAS search for the recommender system. It's a very large application. You have to really search not only the convolution layers but also for the connected layers, embedding scheme or so on first. I'm not going to all the details. You handle all the different types of connectivities with the different types of interactions or operators, and also the different size from very small one to very large one. You have to balance all of this. So, and also very time consuming for the search, but we got very good result, and which has been deployed to the product of the Manta. And we are continuing doing our design in this particular research. I think we have about 1 hour, so maybe we can have a break, maybe, because we'll give a lot of information, and next we'll talk about the code design for robustness and putting them together. I don't think we'll talk more than that. Yeah, so that's I will maybe stop somewhere. So in the putting together. But let's come back about 11:10. Okay, so give people a 10 minutes a break, and we'll continue talking about the code design for robustness. Yep. See you guys in 10 minutes. Okay, so we're back. See me?
Yeah, we can.
Okay, so let's continue talk about the code design for the robustness of the AI hardware, especially for the emerging devices. We just talk about we are able to use some emerging devices to represent the neural networks weights or the parameters. Since those devices are nanoscales, the resistance or the conduction of these devices are very non-ideal. That basically means, number one, each time when you access the device, the demonstrated resistance are different, which we call the cycle-to-cycle variation. Another one is we call the time shift, which means over the time or over the operation, the resistance of the device will actually change. It's actually give us a lot of difficulty, how we are able to handle these vulnerabilities. Not even talk about when we are manufacturing the device, the resistance of the device will change due to the variability of the device thickness, the shape or the size or so on first. So one way we could do is we can actually shrink the size of the crossbar. For example, we don't want to have n by n crossbar. Rather than we can do the model reduction so that we can decouple the matrix to two different smaller irregular matrix so that we're able to reduce the dimension of the matrix and reduce the variability along the one dimension. We can also somehow statistically compensate this variability by assuming where's the noise. So we are training the neural network will already consider this noise. We can do the hardware fix. We can say, okay, we can replace this device with another device, or during the training, if we know some devices are totally dead, like they're open or short, we just let this device represent 0 and 1, and we still be able to train the whole neural network to accommodate this design, which we can retrain the neural network, but adapt to these defects. But if you carefully look at, this dynamic noise, which means this noise will generate it in the operation. There are two different noises we need to consider, which we call the perturbation of the weights, which means resistance of this device. The first one is a high amplitude noise due to the frequency and the temperature. If we increase the temperature, this semiconductor device will change their behaviors or generate some noises. We also have this stochastic noise, okay, including the thermal, shot, or something first. Those are some random noise. We also have the high resolution, noise, which means, if we have a larger and larger resolution, that we want to represent the multiple bits in one cell, we need to fix, the resistance levels to the multiple one. And since we have a fixed range of the resistance of the device, then the noise margin between different levels will shrink. So that is another one we need to deal with. Okay, so in 2021, our student Xiao Xuan came up with something called the RM-based stochastic noise aware training. So basically, or the RUST-NA. So basic idea is, we're going to analyze the distribution of the noise under the frequency and the temperature setting, and include the relative conductance change to the RNN cell during the training. And then we're going to apply the Howard sighting to the quantization steps so that we can adaptively quantize the different levels, as we just showed before, to minimize the impact of these noises. And finally, we may have the multiple copies. We can do the voting for the last fully connected layers, to basically amortize the impact of noise between the different outputs of generated design. And the result will show that running on the different clock of frequencies may have a higher and higher noises, and running on the higher temperature start with higher noises. All of them will actually reduce the accuracy. But the purple one shows the rationale with the voting without the blue one, so without voting, so they can always improve the performance, by comparing if you do nothing. Okay. However, given the design objective, conducting robustness, efficiency, because we understand the robustness and the efficiency are always the trade-off. You can always, improve the robustness by paying for the efficiency, like you have the voting or without voting, training the different way, or using, so can we really determine the different quantization levels or something first? So can we really determine and select the ideal hardware configuration by doing this? The answer is yes. It's basically nothing else but the multi-objective optimization. What we can do is we actually can leverage the existing design objective optimization to showcase. So, and this is a chart showing the different trade-offs. You have a difference in accuracy or AV overhead, execution time, energy consumption. They all end up with a different goal and different optimize the configurations. So we use the continuous fidelity max value entropy search, which is a very well-known, the multi-objective optimization design for the case. So we actually can apply this technique by using the min max value entropy search to find out the optimal candidates design. And the results, like we show here, basically show that you have different AVS with a different inferencing accuracy target, and different energy, different latency. You will end up with different trade-offs, and we'll be able to find out the Pareto optimal result. And you can pick the one which you want based on your targets. And that's the one example is you can see that the high cell resolution sighting or the high frequency sighting appears in the Pareto front due to this actual design, which means they give us the good either robustness or good performance by paying for one the other. So that's the design. Okay, so far we finished all this hardware thing. Now let's move to the system design, which is the fun part. If we have this hardwares and how we're able to incorporate this hardware design, basically the edge devices into the edge system. The challenge one on the edge, as we all know, is actually resource constraints. We are facing the growing size of the AI models. Even we understand we have a limited capacity on the computation. So that's actually publication data plus the number of parameters for the models. We have larger and larger models, not even talking about the larger and larger models that we are facing now. And now we have to fit our model into the edge devices. There's another one we actually can deploy the federated learning into it. And when we are doing this design, there are some domain-specific instruction, which means you have different applications, have different knowledge, which are going to affect the operation of the design. And also in the language, you have emotional tones, like culture factors, all kind of stuff, which we call the personalization, will become the must in the design. We need to handle this personalization when we're deploying our models into the device. So we eventually, each device will have their own models, highly customized for the data the device is processing, and and also running. So the three is about the privacy and the security. So the edge device hold the private data. In your cell phone, you have a lot of private data you don't want to share. And we need to prevent, this data from being. So the multi-device, the multi-device edge computing scenario, like a federal learning, allow the malicious device to conduct a virtual attack. And because we already include many devices, and some of them may be malicious, we need to bring another challenge to ensure the security of an edge computing station. I have many topics. I'm not sure you can finish all of this, but we'll see how much we could do. We're probably going to finish until the large language model personalization on the edge. Okay, so to give people some background about a federated learning, which is the most popular distributed learning framework we're using for the AI now. Think about, we have a lot of users. They have their own data which they're willing to share to a certain degree to the AI models they're running. They can actually train the model based on the data collected from the different users. But they also want to make sure we have some privacy protection so that we don't really leak all the sensitive information to the cloud, which is running the information. This federated learning technique actually allows the users' updates are aggregated to form a consensus change to the shared model after the procedure is repeated. We train the model distributively, and it can be used for the bank, it will be used for some medical or for any other applications. But training a model like this can be very costly, especially consider the communication efficiency, because the total communication cost will be the communication round. We need to send data to the centralized server times the number of parameters per round, and times the code words length per parameters. If we want to run the VGG16 on the internet for the different clients, we may need to run those things with 9,000 rounds, to collect all this data into this centralized server, and we have 138 million parameters need to be sent, and each parameter will be the floating point, which means 32-bit, and we basically need to transfer about 500 terabyte data between the clients and also the server. It's very costly. And more than that, the device frequently generate and collect data in a non-identically distributed manner, which we call the non-ID. That basically means, the data collected by each device are correlated, but not exactly the same. Okay, you cannot treat them independently, like Gaussian and so on first. This is going to create some issues that if we simply use a very naive, the federated learning framework, like a Fed average, you just want to average all the updates, from the different devices by treating them as independent data or independent model, you get a very bad result. We need to consider, the personalization and the correlation between different data. So what we proposed, 2 years ago, we called the lottery federated learning, which are trying to improve the communication efficiency and achieve the personalization and the non-ID side. So for non-ID plus personalization, we try to use the lottery ticket subnet for each device, which means in this particular design, we have the overall neural network. But when we are deploying the neural network to the different device, we only deploy the subset of this neural network, which we call lottery ticket subnet. It's going to be part of the complete neural network, but still be able to perform well for the task on the different devices. And it's also be communication efficient because only to transfer the parameters of the subnet rather than the whole net to the cloud to do the averaging between different updates on the different networks, for the training. Now, how we're able to do this? So if the local lottery ticket network learning will be like this, we could download this network from the global server. We don't have to download all of them, just the weight we need to train. And we'll prune and resize the subnet if the accuracy is larger than some threshold, and if not, we'll continue retrain the neural network so that eventually we'll end up with the simplified the neural network with a satisfied accuracy. So R here basically means a reduction. That means how the ratio for us to reduce the size of the neural network. So personalization preserving aggregations is another technique, because when we're sending the neural network, the lottery ticket neural network to the global server, it's only include a part of this all the weights we need to aggregate. So what we can do is we just aggregate the corresponding locations of the neural network, and by taking the input from the columns which use the neural network include this particular location. So that's what, in other words, only the overlapped element will be aggregated. So by doing so, we also reduce the computational cost because we don't really aggregate all the input. So let's look at the result. Well, let's say we have only 10 to 40 samples on each device because we assume we have a limited training data. We also have only 2 classes of this example on each device because we don't want the device to have all the classes. That is not usually the case. They only have the part of the classes. And data unbalanced. The data volumes are different across classes on each device. Okay. So the baseline is we train everything the local by assuming there's one server have everything, all the data from all the columns, which is the ideal case, okay, but not the practical case. We have fed average, which is the very naive design. Say we take all the input, we do average, we send them back. Or we do the LG fed average with a global model with local fine-tuning. We'll compare 2 things. One thing is the inference accuracy, and then one is the communication cost. So we're trying to see what are the trade-offs in between these 2 metrics. We train CFAR10 for 2,000 communication rounds. And the accuracy increased by 13 to 15% compared with LG fed average. That was the state of the art. And the communication cost is reduced by 34 to more than 50%. So that's the power of our design. Of course, if you have a higher number of the example per class, we'll have a higher performance because we have more data to train, right? So that's the result. But no matter what, they give us the good accuracy, the lower communication cost or so on first. And the more interesting, you have the unbalanced data, which means, even we have 2 classes on each device, the number of the samples per different class are different. Balance means that they're one to one, which means we have an equal number of the samples per class. Unbalanced means we have unequal data, the number of the classes. So unbalanced 0.5 means we have maybe where the ratio between the number of the samples per class is actually 1 to 2. So if one have 10 samples and then one have 20 samples. Unbalanced means we have 5 or 120. You can find out that the unbalanced data will give us the worst result. But we always have performed much better compared with, let's say off the art. Okay, so can we do even more than that? Because here we actually reduce the computation cost, the accuracy, but we did not consider computational cost. Even we roughly reduce the computational cost a little bit because we actually compute the subnet, but it's not, yeah, but it's not that sufficient because it's basically at the same level, same magnitude of order of magnitude. So we came up with another solution called the fat mask. The fat mask do something even more aggressively. They say we have the same networks, but rather than we train the neural network, we actually train the binary mask, allow the part of the weights to be exposed to the neural network, which is going to participate in the computation. So binary is 0, 1. The 1 means we allow the weight to show up. 0 means we're actually going to block this weight. So by doing so, we're actually going to have, this mask weight or mask neural network, to be deployed to the different devices. And each device will only train a binary mask, which is going to manipulate the location of different different 0, 1, for this binary mask. You may question why we can do this, because if the number of the words of the neural network is large, then the search space of this binary mask are very, very large. So there is a possibility we actually can somehow train the binary mask to represent the personalization rather than train the neural network and still be able to give us a reasonably good performance. So the result will be like, so the design will be like this. We have the device which are processing different data. So, and we going to send this binary network to the central server. They can do the mask aggregation rather than do the weight aggregation. The binary mask will be the element-wise applied to the frozen parameters to generate the personalized and structural response models. There are some design talk about how we can do the structural response by binary mask, because we actually can perform the structural pruning on the binary mask to generate a small architecture and deploy it on the device. And if we do the mask aggregation that we show here, well, again, we only do the aggregation on the overlapping locations. In this design, for example, if we see the yellow and the blue, and we will actually aggregate them to generate the green, binary mask. And if there is only one show up and there are no any other overlapping, we cannot just algorithm with 0. We actually need to keep, the original kernel and reassign it to the device. Okay, so that's how we're going to do the mask aggregation. The results show on the 3 or 4 different data sites show that this fat mask gives us the best trade-off between the inference accuracy and also the communication time. And we show here. So the right star is our result. Ideally, we want to see the highest accuracy, which actually push on the right, but the lowest communication cost push on the bottom. So if we have the fat average, for example, they give the moderate accuracy, but a very high communication cost, which is the green dot. So we have a binary neural networks, which will give us the lowest communication cost because it basically transfer nothing but the binary information. But the binary neural network, you're to give us very bad performance or the very low accuracy, which is the brown brown dot I will show here. And this is actually going to improve the performance and reduce the energy consumption because we need to only compute the binary neural network. So inference, speed up increased by a couple of times, by 1.4, 1.5 times. And the energy saving will improve by, energy efficiency will improve by 1.6 or 1.5 times, like we show here. And the binary still give us a highest of speed up and also highest energy saving, but that does not make much sense because the accuracy drops significantly. And the fed mask model also reduce the size a little bit, which is required by the memory, because we need to store the binary mask rather than the original D, and so on first. Okay, so that is another way to handle the computational and also the communication efficiency. Let's talk about another topic, which is the semi-asynchronized federated learning. Why we need to talk about this? Because in the synchronized federated learning system, we have to synchronize, the training of our neural network at the end of each epoch. It's be very efficient and robust because the central server need to be waited for the slowest device. If we have the neural network, the same neural network, which are applying to the different devices, and there may be some device which can run very slow. So we have to wait until this device to generate the output. And then maybe our device already finished a long time ago, we have to wait until the slowest one to finish. And even worse, some devices may drop the line. They may actually crash on the networks. So people came up with asynchronized and semi-asynchronized federated learning, which show the accuracy drop because we have to asynchronously aggregate this neural network. And it's usually be an unrealistic assumption. For example, the server know when the device will complete the training. Well, it's hard to know. How could you know, when the server will, when the device will finish, right? And also the limited scalability, because you have more devices, then the asynchronization will be very bad. Okay. So we try to do the following thing. Number one, how we're able to elevate the performance degradation of the global model caused by the stall model update, which means the slow device. How to determine the synchronization time point in the realistic setting, because in many cases, we probably don't want to wait the tail of the device to finish their computation. And the third, how to deal with the device with extremely limited computational and communication resources. Okay, so those are the three challenges. Let's talk about the number one, performance degradation. So the convergence degradation mainly comes from the unbalanced uploading frequency of the fast and the lagging devices. So if the uploading frequency of the device is unbalanced, then there will be an error involved to hinder the convergence of the design. So we're going to propose to reduce the local training steps of lagging device, such as they can finish the local training task faster and to upload their updates more frequently. So one way to do it is so-called the training configuration scheduler. So the fewer training steps will obliterate the contribution of the slow device during the aggregation. Then what we should do is we actually should predict if the slow device can really update more frequently what it's going to look like. So to solve the problem, we increase the learning rate of the slow device by same time of the reducing the training step, so that we can really give the prediction of how the slow device will impact the training, and we show here. Okay, here if the brown will be the operating training, W1 will be the slow device. So what we can do is actually can give them the 3 times faster, so we know how we can do this. Okay, so the second one is synchronization. The significant information needed to schedule the end time of this communication run is the anticipated end time of the local training of the device. But do I need to wait until then to finish? Probably not. Because the device may have a dynamic computation power, which will make it necessary to profile the device before starting of the training each round of the participation, and we can somehow predict when most of the device can finish. So we created something called the end time predictor to that into collect the training time of the starting step and then send the set of the time to the server. So to avoid incurring the additional computation overhead, we profile this and we assume there's a distribution of the end time, and we'll say, hey, after maybe 95% of the confidence time, when we'll say this is pretty much the end of the time. Don't wait for even longer. So what I can do that is. So third one is actually we could handle the gene stragglers. So we're going to design distillation module so that we can distillate, original network, to a smaller one and running on this stragglers. And after that, we'll actually have the infusion model to reverse, this is reduce the size model back to the regional size model and do the aggregation. By doing so, we actually can eliminate the trade-off, eliminate the irregular contribution from the straggler device. We run our experiments on the real devices and profile them, and we run a simulation, for all the result. The result basically show that our result is actually the right star. If we look at the trade-off between the normalized times cost and inference accuracy, we actually have the best trade-off between them, which will give us the lowest normalized times cost and highest accuracy. And we show here. For any others, so they just even cannot give the good accuracy or even consume much larger computational or communication time, which show here. So that's the result. Okay, so let's talk about maybe the last topic today, which is large language model personalization on edge. The traditional method of training a large language model such as ChatGPT is to collect a large number of instructions together for the training. If you still remember how you're going to use the ChatGPT, you basically, to write a lot of prompts, and then there's a prompt to give the feedback to the model, and the model will follow your guidance to generate the output. However, what if millions of users prefer not to share their instructions, and these instructions may contain the private information? A couple of days ago, I received the email from ACM. They say they actually trying to ban the reviewer using the ChatGPT to polish their review because they worry about this will actually relate the sensitive information from the original manuscript. Okay, so what if the companies are reluctant to share the instructions containing their core technology and the intellectual properties? It's be the news talk about the Samsung people use the ChatGPT to come up with meeting a script, but actually going to leak the sensitive information regarding the science of manufacturing. So what if the country's government regulation disallows the transfer of the data outside its border, preventing the combination of the instructions from the different countries? We need to handle this. So keep the sensitive private data locally on the edge devices and do the federated learning. That's maybe the only solution to do it. The federated learning naturally enable the collaborative learning, but with ensuring privacy as we have done. So we came up with, after we built up the federated instruction tuning framework, which allow us to train the models in the federated learning way without exploring those information to the cloud. So this is what we have done. So we actually compare the multiple results. We use a ChatGPT 4 to evaluate our model, which we consider as ideal performance. and local 1 to 3 are locally fine-tuned model with a limited instruction, which means that each one has their own instruction. You can only train the model with your own instruction rather than you can collaboratively collect all the instructions from different users to do this work. So the llama is the initial model with no instruction tuning. They train the model and to see the centralized model, and the centralized model undergoes a centralized tuning. So our result basically show that the centralized model like GPT-4 will give us 81 per well. Centralized model will give us the 81% accuracy, and if we run the llama without no instruction tuning, only 67. If we can train the model with instructions in the local, we give 170, 172 performance and per person performance, and our federated learning method can give us 76 performance, which is higher than any other local solutions. It's still lower than centralized model, but we remember we actually collect all this instruction from different people, which allow us to do better than any other local solution with only the partial instructions. Okay, so this can be used for the EDA for sure. We actually already came up with the federated learning framework for EDA, which can preserve the privacy of the training data and also the UE instructions. Okay, I will pretty much stop here. I will build this slide, which is not quite relevant, and basically talk about something more advanced regarding the climb selection or the data sampling. There's a more federated learning based rather than software hardware co-design based. So we'll skip this one, but let's talk about the edge based large language model and beyond. So we summarize some challenges for the federated learning system deployment and propose our vision and the solution in the past. But in general, the large language model, follow some we call the chinchilla scaling rules, which will increase, order of magnitude per a couple of months or so on. First, the instruction following the step-by-step, following step-by-step reasoning. You can do the prompt, engineering to guide the model, or you can even train the model alignment, tuning. So those are the good topics people are exploring, and also people also always improve the reinforcement learning process for these large language models. So I believe in the future, people will start to migrate this large language model to edge devices. Actually, a couple of days ago, one of our PIs of my institute, the MIT Songhas group, already sent me the example to run this so-called tiny GPT, which can run this GPT like model with a llama. Is based on llama on the laptop. So that's people already start doing this. So to conclude the whole talk, there are many things we need to worry about, in this co-design, starting from the more computing unit, resource and utilization, part of the model reduction, memory efficiency, and bandwidth, and also the performance modeling, and also some external constraints like the hardware constraints and the configuration, and also different optimization process like algorithm exploration, basically we pick the different algorithms and knots, and how to categorize performance of different the models, and to the hardware implementation. There another thing I did not talk about today, which is the machine learning for EDA. So, but I believe somebody else may talk about this. All of this, creates a whole framework about the co-design in the AI system. And in our work, we start talking about the circuit design, architecture, compression, knots, and then called the distributed system, and which corresponds to silicon realization, algorithm mapping, model optimization, and system integration. We started our research back to 2011-12 and start doing the neuromorphic computing, especially the resistive memory or the RN based neuromorphic computing. We were the first one came up with a crossbar structure, to map this multiplication between vector and the matrix. And starting from then, we developed the accelerators and structural pruning already designed to this different AI accelerators, then to the specking neural network, to the federated learning, so on and not, so on first, until we already built out the full stack solution in my group to cover all of this. So those are the references which you can read. There's certainly some basketball words or something, but yeah, that's all I want to talk about today. And I'm open maybe for a couple minutes questions if you want to ask. Yeah, thank you. Any questions? Okay. So if no more questions, I will give you back, 8 minutes, for today's education lecture. I hope you enjoyed this. Feel free to send me an email if you have any questions about our research, and we'll be very happy to answer any question you may have. Yeah. Thank you so much, and have a good day. Bye. Yeah, thank you.